Hello everybody, in this video we will be solving problem 12 from chapter 2 of Baby Rudin, that is Rudin's Principles of Mathematical Analysis. What does exercise 2.12 say? Well, it says let K be a subset of R, consist of 0 and the numbers 1 over n for n equals 1, 2, 3, and so on. Prove that K is compact directly from the definition without using the Heine-Borel theorem. So let's start by recalling the definition of compactness. So definition, K is compact if any arbitrary open covering of K so let's say we index over an arbitrary set lambda. So we can write K as a subset of some union of open subsets, and we're indexing using just any arbitrary set lambda. A common mistake when people see this material for the first time is indexing over the natural numbers. So instead of writing lambda in lambda, sometimes people will write n equals 1 to infinity, but it's important to remember that we can index over an arbitrary set. So this is an arbitrary open covering. So K is compact if we can take this covering. So if any arbitrary open covering can be reduced to a finite subcovering. So what does that mean? That is, there exists finitely many lambdas, so let's say lambda 1 through lambda n, such that we can write K as a subset of the union from n, or I should really say j, equals 1 to n of O lambda j. What this means is give me any collection of open sets that I can write K as a subset of, then I can pluck out finitely many, and K is still a subset of this union of finitely many open sets. So this is the definition of compactness. When the problem is saying we are not to use the Heine-Borel theorem, that basically means that we don't want to use the theorem that says in Euclidean space Rn, a set being compact is equivalent to the set being closed and bounded. So if we were able to use this theorem, the problem would be done in basically one line, because we notice 0 is a limit point of K. It is the only limit point of K. So K is closed because it contains 0. And it's also bounded because it's bounded below by 0 and above by 1. So K being a closed and bounded subset of R implies by Heine-Borel that K is compact. So how are we going to prove that K is compact directly from the definition? What we want to do for these kinds of problems is consider an arbitrary open covering of K. So let's start the proof. So let K be a subset of the union of lambda in lambda, O lambda. Maybe I'll make this look like a capital lambda. Be arbitrary. And where O lambda is open in R for all lambda in our indexing set. Okay, so we have an arbitrary open covering of K. We need to figure out how to pick finitely many of these lambdas so that K can be written as a finite union, or written as a subset of the finite union of these open sets. So because 0 is an element of K, and K is a subset of this union, there exists lambda prime such that 0 is in O lambda prime. So 0 is in O lambda prime, and we're going to notice now that because 0 is a limit point of K, well, let's back up a little bit. So 0 is an element of O lambda prime. So O lambda prime open What does this mean? A set is open if every point it contains is an interior point. So every point x in O lambda prime is an interior point. What this means is I can find some small positive delta such that if I draw a delta neighborhood around x, that's still entirely contained in O lambda prime. So O is an element of O lambda prime, implies there exists some delta greater than 0 such that the delta neighborhood around x, or 0 in this case, is a subset of O lambda prime. Now let's draw a number line. So here's 0. If I draw a delta neighborhood around 0, I go delta units to the left, so here would be negative delta. I go delta units to the right, here would be positive delta. But notice that this is just the open interval negative delta to delta. So negative delta to delta is a subset of O lambda prime. Now this is where we're going to start using the fact that K contains 1 over n for any natural number n. So notice that let's say 1 is over here, and maybe 1/2 is over here. At some point, I'm going to move to the left of positive delta, let's say 1/3. And now every n greater than 3 is going to be contained in the interval 0 to delta. So like 1/4, 1/5, 1/6, and so on. And because the natural numbers are unbounded, I'm going to get arbitrarily close to 0. And on top of that, negative delta to delta, in this case really 0 to delta, is going to contain infinitely many elements of K. So notice, negative delta to delta contains infinitely many elements of K. So how do we formalize this idea? Well, we notice that delta is just some positive number, and if 1 over n is contained in 0 to delta, then 1 over n is smaller than delta. So notice, if 1 over n is strictly less than delta, then 1 over n is contained in O lambda prime. And that's just because 1 over n is then in the interval negative delta to delta, and that's a subset of O lambda prime. So let's go back to this inequality here. So if 1 over n is less than delta, this happens if and only if n is greater than 1 over delta. And remember, taking 1 over delta is well defined because our assumption is that delta is greater than 0. So notice 1 over delta, this is some finite number. And we're saying, okay, well, n is greater than 1 over delta. So because the natural numbers are unbounded, this means that there are infinitely many elements of K that are contained in 0 to delta. So that justifies our statement up here. Then notice negative delta to delta contains infinitely many elements of K. So now we need to consider the case, well, what about the elements of K that live outside of negative delta to delta? So if I have an element of K and it lives outside of this interval, well then 1 over n is either equal to delta or greater than delta. So if 1 over n is greater than or equal to delta, this happens if and only if n is less than or equal to 1 over delta. And in this case, 1 over n is not contained in negative delta to delta. So if n is less than or equal to 1 over delta, we'll recall that the natural numbers are bounded below. So because natural numbers are bounded below, there exists some capital N, so there exists n such that for all m greater than n, 1 over n, or rather I should say m, is greater than 1 over delta. What does this mean? It means there exists some capital N such that n is the largest natural number for which n is less than or equal to 1 over delta. So let n be the largest natural number such that n is less than or equal to 1 over delta. So then there exists 1, 2, all the way up to n elements of K not contained in negative delta to delta. So notice that there are finitely many elements of our set K that can't be covered in this open interval. So we know that this union over lambda and lambda of O lambda, well, this in theory covers everything in K. So let O lambda I be such that O lambda I contains 1 over I for 1 less than or equal to I less than or equal to capital N. And again, we know these exist because we're taking them from this arbitrary open covering of K. So now we've considered two cases. We've considered what happens if I have an element of K that's less than delta. And I know that that set of elements can be covered by O lambda prime. What happens if I have an element of K that's outside of the interval negative delta to delta? Well, I've picked finitely many open sets from my original covering that can cover those points. So K can be written as a subset of O lambda prime union, big union from J equals 1 to capital N of O lambda J. So because the union of lambda and lambda of O lambda was arbitrary, and we were able to reduce it to a finite subcovering of K, we conclude that K must be compact. And this completes the proof.